Because we're in Japan, like, I want to ride my bike. Greg said it was fun. Not Greg Roach, Greg Stroud. Okay, with an R. So, what was I talking about? Oh, yeah, so we got these new pants.
You're talking about
Where'd you get them at? eBay. They were somebody else's pants. With shipping, $10. So you know they're good.
That's a steal.
Oh, it's steel. These pants are like $80. So why don't you just go to Ross?
Just buy some Jinkos.
Buy some Jinkos.
Good question. I don't know.
I don't have like infinite money, but I would buy you Jinkos, and then we could go to the Los Margaritas.
We can go to Las Margaritas.
Yeah, I'm good with that.
Send Jinkos or not.
Okay.
Mr. Kessler, if I were to get you
Did
a
I
Naruto,
say that?
No, just us.
No. You don't understand hints.
Wow. He really does.
What?
Mr. Kessler, if I were to get you a Naruto headband, would you wear it?
During school, probably not. Outside of school, certainly.
How
I'll wear it during this class sometimes.
Would you wear it to lunch on
No.
every Thursday for the rest of the year?
No.
Why Thursday?
Yeah,
No.
it's a Thursday.
Today's
Today's the first
Thursday.
day.
Today's Thursday.
But we didn't give it to him Thursday.
They're gonna fire me any day now.
Naruto Neener Day.
Naruto headband. What is that? Oh, it's Naruto. Oh, that makes sense. It's
Then you
Naruto.
Then you just gotta show him your hand moves.
I forgot what they are.
There-
I think I did a little-
There's one with like 2 fingers.
Oh, Little Rascals? Little
Like
Rascals?
that.
Alright.
Skirt. I said
You heard about the synchronized book drop?
yes.
Yes, I tried to do it in Algebra 2 last year, but Isaiah wouldn't do the call.
Wouldn't bite?
He wouldn't do the call for it. He had a plan. I was like, Isaiah, do it. He's like, no, I'm not going to do it.
What a loser.
Smart man.
You said last year.
It's not funny.
Yeah,
Count it out.
What was last year?
No, it was this class
You gotta
last
do it
semester.
better.
What?
Isaiah, it was last semester.
Last year.
Isaiah was just like,
You're such a retard.
I
I know it was.
No, it
Thanks,
was
team.
last
Can't be
semester.
obvious.
what would you have to do to make it not
We're in
obvious?
2016.
Like, hey, as soon as
Yeah, I
the
know,
teacher,
I was
teacher
calling
puts
her.
the pencil to the board for the first time, upon contact of pencil to board, everybody drop your book. That would help. Or, upon contact of pencil to board, everybody fake a seizure. Call that one a synchronized seizure. Not what you want to do.
What if we?
Synchronized seizure, not everybody will commit to, and you'll be the one person faking a seizure. To the office.
No, that'd be cool though if everyone just stopped moving. So like no one moves.
Or as soon
It'd be.
as you take your cap off your water bottle for the first time, everyone gets up and leaves the room.
But you have to leave your shoes.
Lock the doors and give a twist. Oh, well, all zeros.
Oop.
Alright, here we go. We are not going to take time to do a simulation activity because we got too much to cover. Y'all got to understand humor. Humor is good when it's unexpected.
That was unexpected.
No, it was pretty expected.
Alright. So suppose x bar is the mean of a simple random sample of size n drawn from a large population. Hopefully you already know this from yesterday, and hopefully because you've seen it in the book.
Whoa.
With a sampling distribution, we know sampling distribution is the distribution of every sample's statistic, and that statistic can change. So yesterday we talked about sampling distributions of p hat, meaning every single possible sample's proportion. Now we are talking about the sampling distribution of x bar, meaning every single possible sample's mean. again, these two formulas are on your formula sheet, you just have to know they are there. Also, please, look at them enough that you can read the notation and know what it's saying. That says that the mean of all the X bars, the mean of all the sample means, will be equal to the mean of the actual population. If you look at the mean of the sampling distribution, the mean of all the sample means, the mean of the means will be equal to just the mean of the entire population. The standard deviation of the sampling distribution of X bar is the standard deviation of X. What's that?
Of the
The population. Now again, you should go ahead, if you're understanding this at all, hopefully that's making you think, oh, wait a minute, we got a problem here. For me to find the standard deviation of the sampling distribution, I've got to know the standard deviation of the actual population. But if I know the standard deviation of the actual population, why in the world am I doing this? We're getting there. Right now, just trust that that's what we know. The standard deviation of the sampling distribution is equal to the standard deviation of the population divided by the square root of n, square root of your sample size.
Are we gonna?
Again, this only works if n is less than 10% of the population. Those formulas are on your formula sheet. Find them, get used to them. Right below the formulas for the sampling distribution of p hat. Again, don't need to know that. Don't need to know if they won't ask about it on the AP exam. If you go to a higher statistics course in college, you'll talk about that. What you do if the sample is larger than 10% of the population. You have to adjust it and use a different formula. You don't have to know that. The behavior of X bar, the behavior of sample means in repeated samples is much like the behavior of sample proportion, or p hat. Just like yesterday when we looked at all the p hats. X bar is similar. The sample mean X bar is an unbiased estimator of the population mean. Meaning when you use a sample mean, it's just as likely to be wrong and guess high of the actual population mean as it is to be wrong and guess low. The values of X bar are less spread out for larger samples. That's the same as it was yesterday with p hat, right? But you took a larger sample, there was less spread in the sampling distribution. Why? Because the larger sample gets, the more it looks like what? The population, so the less it will vary. Bigger samples have less spread. Just like yesterday, if you're not sure right now, look at your formula sheet. Look at your formula sheet. Standard deviation of p hat. The spread of the sampling distribution of p hat was the square root of, what was it, p times 1 minus p over n?
Yes.
Which we said is really just the square root of p times 1 minus p over the square root of n. Standard deviation of X bar is just, what is it on your formula sheet? Standard deviation of the square root of. Standard deviation of the population over the square root of minus p over n. So please notice, what we said is really just the square root of p times 1 minus p over the square root of n. Remember what we learned? If we wanted to cut the standard deviation of X bar, sample size times is just, what is it on your formula sheet? You end up taking the square root of what you increase. Standard deviation of the population over the square root minus p over n. Please notice, what we said is really just the square root of p times 1 minus p over the square root of n. Remember what we learned? If we wanted to cut the standard deviation of X bar, sample size times is just, what is it on your formula sheet? You end up taking the square root of what your problem. Standard deviation of the population over the square root minus p over n. Please notice, what we said is really just the square root of p times 1 minus p over the square root of n. Standard deviation of X bar Currently 10 is 30. What would I need to pay for 1? If you want to cut 3 down to 1, what do you want to divide it by? You want to divide by 3. Right? It's standard deviation, you divide by the square root of n. What would I do? Right now, we've been dividing by 30. So we want to divide by 3 times radical 30. Which is actually what is the radical down to 1. What do you want to divide it by? You want to divide by multiply 30 by. Right? It's standard deviation, you divide by the square root of n. Right now, we've been dividing by standard deviation of x bar from 3 down to 1. We want to divide now by the square root 3 times radical negative 2/7. Which is actually what is the radical down to 1. By half the square root of 30 on the bottom of 35. And I want 3 times the square root of 30 on the bottom is what I want. Right now, we don't want to divide by 30. So we don't want to divide by 3. And then 30 by 3 is the radical negative. It's 30 times the square root of 30. Half the square root of 30 on the bottom of 2/7. Once the 3 times the multiplied by 3. Apply both to the multiplication. We have to of weights in the jars is approximately normal with a mean of 16.1 ounces and the standard deviation of 0.15 ounces. Without doing any calculation, explain which outcome is more likely. Randomly selecting a single jar and finding that the contents weigh less than 16 ounces, or randomly selecting 10 jars and finding that the average contents weigh less than 16 ounces. What's the difference in the two situations? Sample size. So if my sample size gets bigger, what would you expect to happen? It's going to look more like the population. Now, what I'm hearing most people say is just referencing the normal part. But the normal part isn't the question here. So let's go back and read the question. Without doing any calculations, explain which outcome is more likely. Randomly selecting a single jar, meaning sample size of 1, and finding that the contents weigh less than 16 ounces. Or randomly selecting 10 jars, sample size 10, and finding that the average contents weigh less than 16 ounces. What did you say happens as sample size increases? It looks more like the population. There's less variation. Okay. So which one's more likely? That you pick 1 and its weight's less than 16 ounces, or you pick 10 and their weight's less than 16 ounces? You can't make the decision unless you look at the population. By looking at the population, what would we expect to see when we pick jars? 16.1, right? Now, will it be 16.1 every time? No, that's the average. But if I've got to take a guess, I'm guessing it's going to weigh 16.1, correct? Which is going to be more likely to be off? Picking 1 or picking 10 and taking the average? 1. Because taking 10 is going to look more like the population. Now, that doesn't mean that 1 would definitely be more off than the average of 10. It just means it'd be a lot more likely for 1 jar to be below 16 than for 10's average to be below 16. Does that make sense? Okay. I'll uncover it. I don't know if you got blanks or what you got. Put in your own words or fill in blanks. Averages are less variable. The same thing if I said, okay, or sample of size 100. That'd be real unlikely, right? The bigger the sample size, the more it's going to look like the population. The bigger my sample size, the less likely it is that it's off from the mean. Because being below 16 ounces is more than 6 standard deviations left of the mean. It's pretty unlikely. It would be real unlikely for 10 jars to have an average below 6 standard deviations of the mean. Anybody got what they need? Okay, so if we were going to find the probability of those two events, think about what we're finding. The probability that x is less than 16. I'm going to give you a test back today, and something I've noticed is this. A lot of you aren't naming what x is, or you're not naming it correctly. So first of all, what is x? Not in this problem, just in general. X is what?
A variable.
A variable. What does a variable have to do in its name? Vary. Some of you are telling me like x equals 3 people. It's not a variable anymore. So what does x stand for here? The weight of contents of a randomly selected jar of peanuts. That's what x is. Don't put x equals 1 jar. That's not a variable. Now I know what x is. X has to vary to be a variable. The other thing I'm not seeing on that test is this. You're not telling me about the distribution of x. On that last test, if you told me what x was and then you wanted to use binomial, you had to tell me x is binomial. Just like you had to tell me x is normal. Or x is geometric. You can't just jump to treating it like it's normal if you haven't told me it's normal. So, B part. If I want to find the probability that one jar, sample size one jar is less than 16. First we gotta define X. X is the weight of the contents of one randomly selected jar of peanuts, and X is normal. How do I know? How do you know it's normal?
Just said it.
It said in the problem. You don't have to prove it if it says it in the problem. X is normal with a mean of 16.1 and a standard deviation of 15. Then I'm seeing people leave out this first part. I gotta be able to follow. Here's what I'm doing. That's what X is. X is normal. I'm gonna find the probability that that variable is less than 16. Here's how I did it. I need to know what that is, what that is, what that is, what that is. We can't just jump around and have some of that. What are we finding? The probability of that X, that the weight of one randomly selected jar is less than 16.
Why do you have negative 100?
Because I need a lower bound. What would you say to that?
What?
What would you set yours at if you don't want negative 100? If you're gonna set a lower bound,
But you can't have a weight below 0.
agreed? What would you set yours at?
0.
I'm just covering my bases, going way far below.
Okay.
Yes, sir.
Why are you taking the square root of 10?
Why am I taking the square root of 10? Because, look right here, Andy. On the second example, are we talking about a sample size of 1?
No.
We're talking about a sample mean, right? If I want to find the standard deviation, I'm using the formula from the formula sheet. What's my sample size? 10. Alright, and the second one, did we pick 10 jars of peanut butter? Okay. So, divide by the square root of 10. In this one, we divided by the square root of 1, but that's just 1. Okay, these are two different problems. That's for when I'm picking 1 jar, this is for when I'm picking 10 jars. Alright, see you after lunch.